good day, geometry. We have reached the end of our curriculum, last unit anyway. It's going to be on circles. Set the best shape for last. We've talked about triangles, talked about quadrilaterals, and all of that stuff will be coming back in circles also. But we're going to start pretty basic and just get a whole bunch of definitions up here. Some of them you know. See if I can fit all of them. That should work. Some of them you know. Some of them will be new. But let's start out with radius. What's the radius of a circle? Bubbles. You like the shape of a circle. Bubbles around. What's a radius?
I don't want to answer anymore.
Oh, okay, fine. Peter.
The distance to the center of the circle.
Right. A radius is a segment from the center of a circle to a point on the edge. And I say edge kind of tongue-in-cheek because a circle, of course, doesn't have any sides, therefore doesn't have any edges. Just for lack of a better word, right? A radius goes from the circle, center of a circle, to a point on the edge of the circle. Doesn't matter where that point is on the edge of the circle. A radius, like the hands of a clock, could just be any direction, right? But from the center to a point on the edge. And the radius matters. We use it in finding surface area. We use it in finding volume. We use it in finding area. In general, it's a very widely used metric. How about a chord? This might be new. The chord of a circle. Okay, the chord of a circle. We're all going to learn something new today. Is a segment going from a point on the circle to a second point on the circle. I don't even need to use the word edge. I'll say on the circle. A segment going from a point on the circle to a second point on the circle. Second point on the circle. Okay, so an example of a chord might look like this. Okay, that would be a chord. Notice it is a segment, so it does have endpoints, one on the circle, another endpoint on another part of the circle. Another example of a chord might be something like, that. I don't know. Okay. Yeah. Blake. Yes. The diameter is what?
A line that goes from one point of the circle through the center of the circle.
So since the diameter can be measured, so use it for things like circumference and areas like that, it can't be a line because the line has no measure. So it is a segment. But tell me more.
A segment from any point on the circle that runs through the middle all the way to the other side.
Yes. And now that you've been given the definition of a chord, a diameter is really just a really special chord, right? Because the diameter, as you know, starts with a point on the circle, runs through the center to another point on the circle. That's the same definition as a chord, with the extra caveat that it passes through the center. So the diameter is really a chord, just a super special one. This is the official mathematical definition. A super special chord that passes through the center of a circle. Okay, a super special chord that passes through the center of a circle. You know what this looks like. You've used it before. You started labeling it probably as early as second grade, right? And a diameter is marked by making it into a little Pokemon ball. Okay, you actually mark the center of the circle. If the center isn't marked, you can't say for certain unless you have other clues whether or not it passes through the center of the circle. Just like a right angle, right? If you've got a triangle, unless that right angle is marked, you can't say for sure, unless you've got other clues, that this is indeed a right angle. So diameter, similar thing. You have to have that center marked. A secant. A secant. Anyone heard of that term before in terms of circles? All right. Well, a secant is a line that passes through a circle. A secant is a line that passes through a circle. So an example of a secant, there it is. Okay, a line that passes through. So we can't measure it because a line doesn't have measurement. However, we could measure the chord that secant kind of creates. If we put endpoints here and here, we have a chord within the circle, but also that chord is part of a larger secant that is passing through it. Yes?
So it's just a secant, a chord, but it's a line.
Yes. Yes, but the only part we can measure is the part that's contained within the circle is actually a chord. Okay? Questions so far? Isn't this fun? Okay. Tangent. Again, not the tangent of a triangle. Yes.
Is it a line that passes through the center of a circle?
No, it is not. That's a good guess, though. A tangent is a segment, ray, or line. So I'm using my SRL kind of a abbreviation here. Okay? A segment, ray, or line that touches a circle at exactly 1 point. Okay? A segment, ray, or line that touches a circle. I'll write that word a little bit neater. Oop, maybe I won't. Touches a circle at exactly 1 point. So what a tangent does, here's our circle. Tangent comes down, just touches it on the end, right? And then continues on. This could be a segment, it could be a ray, it could be a line, it doesn't make a difference. But it touches the circle, it doesn't pass inside the circle at all. Touches the circle at exactly 1 point. Yes?
Could like a ray that could like the endpoint be inside of it, then the line goes upwards?
No. I think what Blake is asking is, could you have something like a ray start within the circle and then go outside the circle and that be a tangent? Yeah. No. No part of the tangent line passes through the circle, so it's entirely on the outside of the circle, okay? But it does touch the circle at exactly 1 point. Right. A point of tangency is the point where a tangent touches the circle. Okay, so that point that I labeled here earlier, this one here, that's your point of tangency. Point where tangent touches the circle. And finally, can those in the back see? Or should I scroll up?
Scroll up.
Okay, are we all good with what we have so far? Anyone still needs to write down notes? We're all set? Okay, I'll scroll down. So much for getting them all on one. I'll blow this up. All right, so common tangents are tangents to the same circle that share a common external point. Tangents to the same circle that share a common external point. Okay. So, for example, we had this. We have a tangent coming up like, just pretend that just touches it there. Okay. And a tangent coming down like this. Okay. They'd be common tangents. They share that external point. Okay. And that's actually going to lead us into theorem 10.2. So skip 10.1 for now. We're going to go to theorem 10.2. Theorem 10.2 has to do with what happens when you have those common tangents. So draw a fairly large circle. It's large enough for you to label. Okay. Give it a common point or a point somewhere out in space, and then draw in tangents. So we're going to have one come up like this, just touch it and pass on by, and the other one come down like this, woo, touch it and pass on by, and we're going to label or identify those 2 points of tangency there. All right. So we've got our 3 points there. Just by looking at this, who can predict what Theorem 10.2 is going to tell us about the significance of common tangents? Anyone have a guess? Yeah. It does make a little bit of triangle, doesn't it? If we connect these 2 points with a chord, it's going to make a triangle. It's not where I'm headed, but you're right, it does. Any other thoughts? Predictions? Well, it turns out that the 2 measurable parts of those tangents from the beginning point to the point of tangency are congruent. Okay? Are congruent. So Theorem 10.2 in words says 2 tangents with a common external point. Oops, I didn't even put a period there. I was just thinking point. Common external point will be congruent segments. Okay? So the measurable part, that segmented part of a tangent from the common external point to the circle will be congruent segments. All right? Other questions? Good questions so far? Okay. Theorem 10.1 also has to do with a tangent. So again, we're going to draw a circle. Ooh, that's not a very good circle. Hold on. I can do better than that. Let's try. That's a little better. Okay. Again, we're going to draw in a tangent line. Ooh, a little wobbly, but we'll go with it there. Okay. Label our point of tangency here. And here's where circles get to be fun. It turns out that the radius of a circle, remember, radius can be drawn in any direction, right? It doesn't have to go straight up or straight down or straight sideways or whatever. The radius of a circle coming from the center, going down to the point of tangency, what do you suppose is created by the radius of a circle and a tangent line? Mackie?
A right angle.
A right angle. Yes! Yes! Okay? Yes! Theorem 10.1 says a tangent will always create a right angle with the radius. I should say a radius because there are several that can be drawn in there. But a tangent line, a tangent will always create a right angle with a radius. Woo. And why is this cool? Because if you look on the next page, you'll see several diagrams, several figures that have right triangles within them, right? Anyone need this? Need these notes yet? Going once, going twice? Okay. So the first part here, you need to use the diagram to identify different parts. What would you say is the diameter of the circle? by labeling, I don't mean like draw an arrow to it or match it up. Actually tell me what part of this diagram here would be the diameter of the circle. What could you write? Mackie? C is the center of the circle. Like C by itself is not a diameter. What makes a diameter, Peter?
Segment VA.
You could write segment BA, which remember your notation for segment is with that segment over it. What else could you write? Because segments have multiple ways you could write them. You could also write segment AB. You don't need them both, okay? But you are actually labeling from the diagram geometrically what makes the diameter. Next one's the radius, secant, tangent, chord, point of tangency, blah, blah, blah. Okay? Then, scrolling down a bit, you've got some questions working with those theorems that we talked about here. Okay? Is DE tangent to circle C? This notation here is notation for a circle. Whenever you see it, okay? It's a circle with a dot in the middle, so you know it's not an O or a 0 or something like that. Is DE tangent to circle C? How do you know? What would need to be true for DE to be tangent to circle C? Let me blow this up a little bit so we can. Right angle, right. Okay. How would you be able to tell whether or not there's a right angle there? Well, for sine, cosine, tangent, you would need some angles, right, which you don't have here.
Side, side, side.
Side, side, side would be for congruent triangles. Okay. Pythagorean theorem, but we don't have all the sides of the triangle, do we?
Yeah.
How? Oh, Blake, you're too smart for me. Okay. This is set up for you to be confused because we have 3, 4, and 2. This 2 only applies to this little section outside the circle. That's why it's in the middle of that little segment there. Blake is saying, well, actually, because this is a radius here, what do we know that distance is? 3. Because it's labeled here with a 3. So what's the entire distance of segment CE? 5.
3, 4, 5.
And then hopefully immediately your brain goes to, hey, 3, 4, 5 right triangle. Do we even have to test the Pythagorean theorem here? No, because we know that a 3, 4, 5 triangle will be right because it's Pythagorean triple. Okay. What's that? Why? Oh, did someone say why? Do you know? Are we all good?
Yeah.
Okay. Okay. So there are certain triangles that that's not one of them. We'll always make a right triangle, and one of them is the 3, 4, 5, where you have leg lengths of 3 and 4, hypotenuse 5. If you do the Pythagorean theorem with those values, you'll see it works out. And so any factor of 3, 4, 5, if we had 6, 8, and 10, that's going to be a right triangle because its base ratio is the 3, 4, 5. Okay? If we had 30, 40, and 50, test with the Pythagorean theorem if you want to, but because it's that Pythagorean triple, you know it's going to work out. Does anyone remember any other Pythagorean triples just off the top of your head? There's one other pretty common one.
5, 12, 13.
5, 12, 13. Excellent. Okay? And there are several others, but anyway. Okay?
I don't remember any of them.
Let's look at the next one. So, to wrap this up, is DE tangent? Yes. How do we know? It makes that right angle. And how do we know that? Because we've got that right triangle that we proved with the Pythagorean triple, or if you went that far, Pythagorean theorem. Next one. ST is tangent to circle Q. Show how you can find the value of R. So this time, we're told that ST is a tangent line, so we know that that's a right angle there. We want to find the radius of the circle. What equation, since we're solving for a variable, we need an equation, right? There's the algebra tie. What equation could we set up here that would allow us to solve for the radius? Guess and check. No. I'm not sure you'd even know how to guess and check here. Okay? Like what would you guess and check with? What would you do?
Keep trying.
Keep trying what? What would you guess with?
Random
Random value. Is R 10? How do I check that, right? I mean,
Yeah.
what would you set up here? Peter? Again, with sine, cosine, tangent, you need to have angle measures, which we don't. Okay? We also don't have two sides of the right triangle here because one side, this 18 isn't QT. The 18 is just from the edge of the circle to point T. We can't use the 90-degree angle. The 90-degree angle can never be used in sine, cosine, tangent. It must be one of the acute angles. Nathan? Pythagorean theorem, right? What do we know? We know that a squared plus b squared has to equal c squared. Because it's the right triangle, that must be true. Our value for a, let's call it r here. We'll make this side a, we'll make this side b. So a squared is a variable, it's r, so we'll just leave it with r there. R squared plus 24 squared. How do we represent c? Gino?
18 plus R.
There we go. And I'm going to put r plus 18. Typically that variable would come first, but either way is fine. And we're squaring that. We need parentheses around r plus 18 because it's r plus 18 is the whole side, and we square the whole side in the Pythagorean theorem, not just a part of it. Okay? Does everyone see where I got this from? This will be a question on your test, so knowing how to set this up. Do you understand why it's r plus 18? Do you understand why it's in parentheses? Do you understand why we're using Pythagorean theorem? Anything?
Yes.
We're all good? Yeah? No? Okay. So our first step, we can't really do anything with the left side here. But back to your old man foil crab claw or boxing days. What does r plus 18 squared equal? Right? Right?
R squared plus 324.
Not r squared plus 324. This is a trap question because it seems like you'd be able to just distribute that 2 into parentheses. But what this literally means is you're taking r plus 18 and you're multiplying it times itself. Does that ring a bell?
Yes.
Foil crab claw box, right? Mackie, what'd you get?
I have a question.
Yeah,
Why are we finding the value of R?
because that's what it says to do.
No, it just says show how to, not to actually do it.
Yeah, this is how we do it.
Yeah, the equation. Why do you have to solve the equation?
Because that's what we do in math, Mackie. We solve the thing.
But the question
got a
doesn't
point.
tell us to.
No, this is just what we do. This.
Just not say fun.
If we don't solve, Mackie, why am I here? What's the purpose of my career choice if all we do is just show how? You must solve, Mackie. Solve for R.
You sound like the
Great.
alien in the Toy Story.
Yep. So whether you foil this crab claw, this box it, either way you slice it, it's r squared plus 36r plus 324. Okay. If you need the lines drawn in, we'll just do old man foil. R times R, R times 18, 18 times R. It's been a while. Hiya, buddy. Okay. Remember that whole thing last year?
It's like the tornado.
I'm getting this.
Now, whenever we get an equation with an r squared, I get a little bit nervous because how do we solve equations when you have a squared variable? Not perm dots. You can't use perm dots because I say this. We have an r squared and an r term. You can't use perm dots then because those terms aren't combinable. We just learned this in my algebra classes yesterday. Peter? Can't take the root because of that r term. If we just have the r squared, we can use opposite operations. Think about it like this. This equation right here is very similar to the form y equals ax squared plus bx plus c.
So are we actually
How do we solve an equation like that? Put your algebra hats on.
guessing check?
No, not guess and check. Gino? No? Boy, the square root thing, it does have a root in it. No, not greatest common factor.
factoring?
Not factoring.
Can I go ask him?
You could factor potentially. I shouldn't say no. You could factor potentially. It's how you find the x-intercepts of a parabola. CO59 from last year. I showed you a song I wrote about it with a wrecking ball. Peter? There it is. Quadratic
Oh.
formula. You always get a little bit. You always get a little bit nervous when you see that squared term because the potential. Shall I bring the potential for the quadratic formula is there? However, you look at this full equation, and why do we not need to worry about the quadratic formula? Why? Great. Yes. The term that makes this a potential issue is the r squared term. But notice we have one r squared term on both sides. That means we can do what, Greg? Cancel them out. Okay? So we dodged a bullet there, and now we don't have to use the quadratic formula because our r squared terms cancel out. So we're left with 24 squared equals 36r plus 324. 24 squared is 576. And so what potentially was a quadratic formulable equation really just turns into a two-step equation. Right? Subtract your constant, divide by the coefficient, blah, blah, blah. What do we end up with? Who's jumped ahead and solved this? 7. Okay? R equals 7. Are there questions on how we kind of spent a lot of time on this model up. We got kind of caught up with how we factor it and quadratic formula. But any questions on this process? Okay. Last one. Show how you can find the value or values of x. We must solve, Gino. We must solve, or I have no purpose. Joey.
You got like theorem 10.2.
Theorem 10.2. What do we know about those two segmentable parts of the tangents? Blake?
The two tangents.
Okay.
You get a
Folks, shh. Don't congratulate anyone just yet. We do know that those two segments are congruent because they are common tangents. So we can set up the equation x squared equals 9. What is the opposite of an exponent, PermDOS people? A root. So you're going to root both sides. And if you put 3 as your answer on the test, I'm going to mark it wrong. Why would I mark it wrong? Peter?
There's a square.
What does that mean?
You have to square the 3.
Well, we square the 3 to get to 9. True, 3 squared equals 9. But why is that wrong? Why would it be wrong in test? Like,
It isn't. We don't know that those are common tangents.
we do know they're common tangents because you've got the right angles here to tell us that they are tangents, and they do come from a common point.
What's your answer? There's only
Will!
one.
Oh
my
God.
Okay?
Yes,
Remember, again, back to parabolas. A square root can potentially have 2 solutions because, yes, 3 times 3 is a positive 9, but negative 3 times negative 3 is also positive 9. Okay? So watch out for that. Watch out. 3, 2, 1, you are quiet. Any questions or comments, concerns, complaints, congratulations, criticisms? What makes it hard? The throwback to algebra? Yeah, the throwback to algebra. Your assignment,
Bro, come on.
bro, make sure you whine some more because you know what happens when you
Wait,
whine.
don't whine. I don't know.
Wait, don't whine, don't whine. On page.
Yes, Sid.
I didn't say that number.
Make sure you finish the top of this this page first and foremost, okay? We did not finish that labeling part. But on page 656, you are to do 21 through 26, and I need work to be shown. If you need to use the quadratic formula, hint, hint, you'll need to use the quadratic formula. If you do, here it is, negative b plus or minus the root of b squared minus 4ac, all divided by 2a.
I'm up for that thing with like weights on it.
Okay.
I think, yeah, I'm kind of like that.
All right, folks, you got a few minutes to work. That's it, man.